We're going to think of volume as a function of height and see what happens when we change height, what happens to the volume. So we have a cylinder, many cylinders with a radius of 5 units. We're going to see what happens when we change the height. So if this is a cylinder with no height, then the volume of that cylinder would be 0. So what we put in here is 0, 0 is one of our coordinates. And then we could build a table as we increase the height. So if we increase the height to 1, then what we have is a cylinder. Let's go ahead and finish this. But now it has some height. So it has a little bit of height of 1. So now I need to use my formula where I have V, the volume, equals radius times radius, r squared, times pi, and we're going to use 3.14 for pi, and then times the height. I know what the radius is, so I can go ahead and plug that in. And when I multiply those together, the 5s, I get volume equals 25 times 3.14 times the height. If I simplify that further, the volume is 78.5 times the height. So if my height is 1, I would substitute 1 for the height, and that means my volume would be 78.5. Unfortunately, in this graph, they're so close together, so far apart, you can't see them. So we got to go way out. There you go, that's 78.5. And you can see it's a little bit off center. So this line is very, very steep, but it does get a little farther away from 0 as we go. So that's what your graph is going to look like. If we want to do that just as an equation, and what we have, we know that volume, which is my dependent variable, equals, and when I do the r squared times pi, I get 78.5 times the height, which is the independent variable, which would be x. So there's our line for an equation or a function of volume in terms of height. What you'll want to do on the next slide is answer this question. What happens to the volume if you have the height h, if you cut it in half? Where can you see that in the graph, and how can you see it algebraically?